Okay, so why don't we start with vectors? So mu is an abelian multiplicative group, written multiplicatively, and it usually is composed of roots of unity of some complex field. And sigma is a group automorphism, and we want to discuss mu valued vectors. So an array of elements from mu, and we would like to discuss Hadamard operation. So what would Hadamard operations be on vectors? So one could permute those vectors, but one could multiply them by a fixed number in the field in mu, and also one can apply sigma to change the elements by some automorphism of mu. And when I came here, this is the idea of a self. It's not traditionally allowed. I was happy to hear many people spoke about complex conjugation. Even yesterday and today, I don't remember the names of the people, but this would be exactly a typical type of sigma. And we would like to find, giving mu and giving a dimension, would like to find all the Hadamard operations on a fixed V. And now we would like to discuss, oh no, it's the wrong direction. Now I would like to discuss the same question differently. Not that the vector is defined, but actually we start with a group, which is going to be the group of automorphisms. So we guess a group, and we guess a subgroup of H sub X of this group, and X is going to be G mod HX. So this is going to be our array of vectors, and we want to map this X into mu. And the action of the elements, the conjugation, is given by a mapping or a homomorphism of G into the automorphism of mu of X. And so it's the same kind of question, but we start with the group. And there are actions, the Hadamard type of actions, on those maps. So first of all, one can permute. And the permutation, how do I make this? How do I show? No. Where do I press to? Oh, I know. I'll just, I'll go this way. So the permutation is given by that much. This is given by, this would be the conjugation, or what the Saf calls a twist. And we would like to identify two vectors if they differ by a fixed constant, which comes out from multiplication by scalars. And the question is, given this setup, if you can find such a solution, then G would embed into the automorphism groups of V, sorry. Okay, so I insisted upon writing this very non-interesting question to all of the people in here. The really interesting case is two-dimensional. Okay, so I just wanted to persuade the staff to add that. The really interesting question to most of the people here is when the array are two-dimensional. So we have a matrix of elements from U that's M times N matrix, and we have the same type of operations. So what are those operations? There is the permutation. There is the multiplication by signs, and there is this twist, like complex conjugation. And we would like to consider all the automorphism groups of this matrix, or we can do it other way around. We can start by guessing direction. Yes. So we start by guessing a group. This is the way Asaf thinks of that. I guess a group, and I guess two subgroups, which are going to be the isotropic subgroups of the action of G on those subgroups, and we're going to get two arrays, X and Y, which are the quotient of those actions. And again, we have those three types of actions which resemble the Hadamard one. This stands up for the permutation. This stands up for the twist, what the Asaf calls the twist. And there is also the multiplication by signs. And two matrices like that are called D-equivalent if they only differ by signs. Okay, and now we can go the right direction. Okay, so now at that point, we kind of said, why should we restrict ourselves to one-dimensional array and to two-dimensional arrays? So actually, everyone here, I think, is interested in two-dimensional arrays. I insisted against Asaf that we put the one-dimensional array, but the really interesting case is any dimensional arrays. So, for example, we wrote it for 3, but it could be for 4 and for 5. Maybe I shouldn't waste the small time that I have. It's just the same idea. You have a group G, you guess a group G, you guess for 3 isotropy subgroups, and you do the same machinery. Okay, so here comes the definition that Asaf likes. He wants to call such arrays cohomology developed if, am I on the right side? Yes, vectors, matrices, and tensors, if the difference between the action of G and the original object is given by those scalar multiplications. So for vectors, the difference is just by multiplying by a fixed number. For matrices, the difference is given by two scalar matrices. And for three-dimensional tensors, the difference between, let's say it like that, permutation and conjugation, and the original matrix is given by 3 types of multiplying with scalars. And okay, so where do I go? So okay. So first of all, I'd like to show everyone, or to discuss with everyone, the fact that this idea has to do with cocyclic matrices. Okay, so a cocyclic matrix, everyone here knows about it more than I presume. And I only want to point out that usually the elements here are written as x and y and x times y. And for some reason, I thought that the formula would come nicer if it takes x minus 1 and y, but it's the same type of idea. And this is the way 2 cocyclic matrices is defined using a cohomology 2-cycle and a fixed function. And here we show that if we take such a matrix constructed in this way, and we discuss the matrix after being acted upon, the difference between the original matrix and the new matrix is just 2 elements. One of them depends only on x, and one of them depends only on y. So this is exactly the definition of cohomology developed matrix. And I think it has some benefits in it, because you kind of, the general idea is that this type of action is dependent on a non-abelian side. It depends on permutation, which is non-abelian, and on conjugation type of, which is non-abelian. And you take all the abelian side into this definition of D-equivalence or phase equivalence for all of these ideas. Okay. Okay. Oh, I got the wrong dimension. Here we showed that we can define a cocyclic vector, a cocyclic tensor, but I think this is only for the future. We didn't really think about that much in a serious way. Okay. So now, so in order to understand those constructions, we have to discuss cohomology of groups, and this is a must. Why is this a must? I didn't write it. Well, Asaf didn't write it here, because if we want to consider arrays which are independent on G, this means that they belong to the zeroth cohomology of this module with respect to G. So it's the zeroth cohomology of G of this module, and the cohomology is there. If we like it or not, if we speak about a different language or not, representation or some other language, but it's equivalent to having cohomology. So cohomology is there, floating in the air, and so we need to discuss cohomology. So there are two exact sequences that we use. One of them is very similar to the the one usually taken in simplicial cohomology. You take, so here we discuss the general case that we have k arrays, right? So x1 is one axis, x2 is another axis, up to xk is the kth axis. But in our most general case, we stop here. Yes, that's what interests people here. But we could do it for any k. And this sequence is exact, and the 0 represents kind of the identity in a sense. And for some reason, which I never followed the techniques of Asaf, he said that this should be dimension -1 and this should be dimension 1, a 0. But I don't know. As long as this is okay and is an exact sequence, I'm happy. And this is exact sequence except of at the end. So where is the end? This is the end. Here you have a kernel, but you don't have an image to go over it. So this is the only place where the sequence may or must usually be non-exact. And then since we discuss matrices, what are matrices? Matrices are maps of our multiple arrays into mu. So we want to make home of this complex into our mu. So for example, matrices would be home of that into mu, and well, that would be a vector, non-interesting case. And so we get a different complex, which is very much related to the previous one, and this is exact, except at the end side. So these are the maps. These are the maps of matrices. This relates to matrices, this to vectors, and so forth. And this is one complex that we need. And another one is that we want the cohomology of group. Cohomology of group is obtained by forming a resolution of the group G. So let's hopefully go to the right direction. So we have a group G, and we form this chain complex. Chain complex. We take all powers of G, and we map them to one another by a very similar type of map. And the cohomology of this infinite chain is just G. And now we form a big complex. So we have this resolution right there, and the other one that depended on the axis, we have it on the other side, and we have a double complex with many maps. And all the idea of spectral sequence, as much as I understand it, is how to deal with diagram chasing in a two-dimensional array of groups and maps between them, which compute. So this is it. And again, we said it in the previous slide, that the homology of the maps complex is 0 everywhere else, and is non-zero when I equals k minus 1. If someone wants, I can go back, but if you kind of understand it vaguely, I'll go ahead because I have many things to speak about. So that's a true fact. And okay, so we want to calculate the cohomology of this big complex. And okay, it so happens that the cohomology of this big complex depends on which it does not depend, but you can do it in both ways. You can either first derive it on the x's side and then derive it on the g side, or you can first derive it on the g side and do it on the x's side. If you do it on the x's side, this is what you get. And what is that? I remind you, for matrices, these are two matrices divided by the diagonal equivalence that Asaf was speaking about. And for three-dimensional, it would be tensors divided by phase equivalence and so forth. And this is the cohomology. And if I happens to be k minus 1, this becomes the zeroth cohomology of G in this module upon which G acts. So this gives the maps of these objects into mu, which are independent by the action of G. So this is the object that we would like to calculate for matrices, in particular where k equals 2. Okay, but then we can derive it the other way around. We can derive first the G side, and then we get many groups, and then we derive them on the x side, and we get this horrible formula And the only way to really understand it is to discuss some cases, because usually when people see it the first time, like myself, it looks like a lot of letters that mean nothing. So here we discussed the k equals 1 case, vectors, which can be obtained this way, but this is kind of a introduction. The really interesting case is when k equals 2, the really interesting case in this place. So this is what one gets after we derive the g direction, and there are two maps. And okay, so this is the kernel. This is the kernel of this map, and this is the co-kernel of this map. And there is a point that I insisted on writing, but I don't know how about the time, so maybe I should skip this point. I have 10 more hours to go.
Oh, you've got another 10 minutes. 12 minutes.
I thought 10 hours. Okay, so I'll just skip this point. So this point, I insisted that we write. Okay. So what happens? What happens if the vector happens to be an acyclic vector? So what's an acyclic vector? Like an acyclic matrix is a case where your axis is the group G, acted upon trivially by the group G. So non-trivially, but this cohomology happens to be 0. So this presumably complicated arrays and maps becomes much simpler. And then there is this formula. Maybe I'll skip it. I have 10 more minutes, not 10 more hours. Okay. This is the formula that comes out true in this case. There's another remark. Okay. This is the really interesting case for most of the people who are in this room, I think, in this audience. What happens if you have 2 dimensions, 2 arrays? So here's the x and the x and y arrays, and you form this, and this is the result of deriving first on the G side and then on the X side, and we want to calculate that group. And all of the idea of spectral sequences is how to construct kind of this group by some information in the middle way. And the information is usually the kernel of that, which we had before, and then you pull it here. It depends on C. Okay, it's a lot of machinery, but there are 3 groups involved. A group here, a group here, and a group here. So this is our two cocycle, which appeared also in cocyclic matrices. And those groups here are also apparent there. And it depends on those 3 groups that survive to the infinity. These are the groups that are going to compose our this H0. Okay, and now see, now is really the point that I think the bells should ring. What happens if X and Y happen to be the group G acted upon by G by translations? So it so happens that those two groups here happen to be 0 by cohomological reasons. And all of this machinery collapses to 2 informations. Only the W, which is an H2, and only this element, which is kind of fixed. And this really recovers the cocyclic matrix as a particular case of our system, of Asaf's machinery, I should say. Okay. Okay, so where did I go? Okay. So far, we spoke about Hadamard matrices, and I have maybe a few minutes to discuss weighing matrices. Shmuel told me he never knew about weighing matrices until recently. So, fellow Israeli. And okay, so weighing matrix is like a Hadamard matrix, but you allow also 0. So the multiples of the line with a different line may become smaller than n if you do it correctly. But then you will have to allow to put zeros inside of your matrix. So before you only could write plus and minus 1 or roots of unity for Batson-Hadamard matrices, but now you also allow zeros. So all of the machinery changes. How does it change? So this we recover before. This is the same as before, but now we take only O, which is an orbit, stands for orbit, only of the points which are non-zero. We want to discuss those. And those points which are non-zeros need not be the full matrix, full array X times Y. And in this case, this chain here, which we had long ago, even for many dimensions, may stop to be exact. And if it may stop to be exact, all of the previous calculations may fail to hold. So, okay. So, okay. Okay. So here are the problems. I hope I have 2 minutes to discuss them. So there's the problem of reducibility, the non-orientability, and then the non-vanishing of the H1 term. And maybe I'll discuss every one of them kind of on one foot. So reducibility is a condition that Asaf found that would guarantee that this would be exact, even if O is not X times Y. And it happens to be a geometrical condition, which is very nice. And I tell Asaf it may be more interesting than the whole idea, because you define a graph, you take all points in X times Y, cross Y, and you connect them with the graph only if X cross X comma Y is in your O. And you get an object like that. And if we go to tensors, one gets more complicated things. You get one edges and two edges, and you get a simplicial space for tensors. But okay, I won't bother you with that. And it so happens that irreducibility is equivalent to this fact that this sequence stays exact. So what's the idea of irreducibility? I think some of the people who spoke today spoke about similar ideas too. If you have, I can draw it, if you have a matrix, if you have your O composed of two squares which don't touch one another, didn't someone speak about those things today? And in this case, it's a reducible O. But irreducible is that you cannot split your O into two different non-adjacent. Actually, the reducibility and the irreducibility amount to the connectiveness or to this graph being connected. So shall I speak 2 more minutes? 6 minutes. Okay, great. So this is about, thank you. So this is about reducibility or non-reducibility. So this allows the calculation to go on. And now, okay, the reducibility is only relevant when O is not X times Y. Okay. Okay. So this is saying nicely what I said kind of hastily. Irreducibility is equivalent to the fact that the complex down below stays the same. Say it again, I kind of scanned through it. Okay, so we came back to this picture. And now how do people calculate those 3 groups that are going to be a composition group for this group that we want to discuss? So actually, one does diagram chasing along not the D2. I think this is the stage after doing the cohomology, but there is a stage before of that. So you take an element here, which is in cohomology. So it's 0. So its map into here is 0. The boundary of that is 0. And if the boundary of that is 0, since this is exact, there are 2 elements in here that go up and hit it. And if those 2 elements hit it, then we are fine here. But now we map those 2 here. And now we want that to be 0. So we want an element from here to hit it. So this is the type of diagram chasing that one does on spectral sequences. And now it so turns out that those 2 elements chosen here may not be compatible here. In what sense they're not necessarily compatible? They're not necessarily compatible in the sense that they survive in the this is the E1 or the E2 stage, but they would not survive to E3 and to E4 because there are many derivatives formed one on top of the other. And maybe they're nice now, but they're going to fail in the next stage. So let's see. Okay, so maybe I'll read aloud this transparency, and I'll stop here. So the information that one needs for Asaf's method for dimension 2 only is a cohomology class W. This stays on the top left there. Those Cx and Cy are the elements that annihilate the derivative of W, and one wants that the derivative of those Cx and Cy into this direction would be annihilated by those elements. And together with that, one forms those matrices. I wouldn't even stop, I'll stop moving those slides. I just said that using that, Asaf formed an infinite family of matrices that we thought that are new. He did it in bits. First, he used the group of projective, and then he used the group of Grassmannians, and then he used the group of flag, and they are all subgroups of one another. So we were happy that there are 3 cases, but eventually they turn out to be 1 case. So this is one thing he did, and then he was able to use. Until that point, he never used this twist, but then he used the twist and was able to form two infinitely many families of Hadamard matrices that we believe that are new to this new. And I know that Reagan here has a table of finite cases, but maybe someone should make a table of infinitely many, of infinite families. So then we could have compared if if the family that Asaf found is in or is not in whatever is known. Okay, so I rest my discussion.